Okay, so let me begin where I left off. I think I was about to show that EMF is equal to, an induced EMF is equal to negative change of magnetic flux. Here I mentioned that this is a statement that is true in general. This is when, say you have a circuit that's evolving, that's moving in time, and the magnetic field could also be time dependent. But this version of the proof, I'll assume that the magnetic field is not time dependent. There's a small modification that makes the proof true as well when you include time dependence. But there you have to use Faraday's law of induction. So we can discuss that in class, or that could be part of an assignment where we all work it out together. So let me draw one diagram, and then I'll draw a more compact diagram. So suppose you have a surface S1. This is the outward normal, N1. And this surface is evolving in time. And let's say it's moving this way, consistent with how Griffiths has drawn his diagram. And sometime later, the surface is S2. So notice, it has moved, it shifted, and also it has changed its size. It could change its shape as well. I mean, obviously there's a shape change. I haven't cut and pasted. Yeah? So it could change size and shape as well. And we're computing the change of magnetic flux in the same direction. So consistent with this, okay? So in this version of the proof, we assume that B is not a function of T, although the theorem, the result is true, in the general case. Okay. Again, to get to the general case, you need Faraday's law of induction. But this result really motivates Faraday's law of induction. And so once you have the chicken and the egg, then you can place them in any order and even ask the question which came before. Okay? So in this case, Faraday's law of induction came before because he observed it experimentally. But it's a beautiful result. So by delta phi, change in magnetic flux, what do I mean? Really, it's a change in magnetic flux, huh? So I do B dot dA, and I'm going to write dA like this. B dot N2 dA. This is through S2 minus B dot N1 dA. Remember, N1 and N2 points in the same direction. So, not in the same direction, but on the consistent side of the loop. That's what the change in magnetic flux is. But B dot dA of any closed surface is 0. Correct? That is because divergence of B is 0. Okay, well, what does that mean? It means S1 B dot N1 dA. This time I have to use the outward normal. Yeah? Oh, consistent normal.
So for the second one, we're using outward normal.
Yeah,
Okay.
because it's for the closed surface. We use an outward normal. So then I get, well, let me write it this way, it's easier. B dot N2 dA through S2 plus, why did I put minus here? It's for a different reason than this one. This is because it's change in flux. This is actually because it's minus N2 because I need an outward normal. And the shaded region in blue as the surface evolves Griffiths refers to as the ribbon. So at any point there is NR for the normal of the ribbon. And it's outward pointing plus B dot NR dA along the ribbon should be equal to 0. This is negative of that. Delta V. Because this is the negative of that. Look at the negative signs. Here the N1 has negative, here N2 has negative. So it's the negative of that. And therefore, I'm not writing it as a separate equation. I can write this instead as so now, I'm just going to use, because I have to take the time derivative. Yeah? So I'm going to use them at slightly different times. So that means this circuit has not gotten enough time to get this far. So what I'm going to do is now, for our conversation, I'm going to consider this much portion. And this is sort of shaded. Okay, so I'm going to look at a portion of dA. Yeah, in fact, let me even hide this. You know it's looping back. I don't want to clutter this. So I'm going to look at small two portions. This is dL. And now imagine a charge. Well, it is moving along the current. Or some dL, sorry, I don't mean. Yeah, there may be a current because of the EMF induced. But also, this is moved to this surface over here. That means it has moved in some direction like this. And I will call this velocity v so that the distance traveled is v dt. If you have a rectangle, the differential area element is nothing but one vector cross the other vector for, a quadrilateral, where the sides are parallel, but it's not 90 degrees. Well, even if it's 90 degrees, it is a cross product, but then it's just length times width, because sine of 90 is 1. Otherwise, it is skewed a little bit. Now, which order do I take the dot product? Do I do this cross this or this cross this? Remember, I want the outward normal. So I better do it from here to there. So with the direction in mind, yeah, this is, oh, no. Right, you're right. Okay, well, let me continue. I will write that as, and this is why. Put the vectors together. Yeah? So then delta phi is equal to B, and this whole thing is dA. So again, I'm putting my vectors together. Yeah.
So the whole thing represents both N2 and, normal,
No.
Normal ribbon and dA.
So sorry, this is only the ribbon. Sorry.
Yeah.
Because delta phi is just the ribbon, the integral over the ribbon. Yeah? So I want to do a little bit of vector identity because I know the answer. There's got to be a minus sign. Okay? But I can do one thing before. First of all, I can take a clean derivative. Yeah? Now, when you have a triple product like this, we can use any cyclic permutation. Meaning, for example, I'm going to erase this part. If I have A dot B cross C, that can be written as B dot C cross A. See, I can't change the order, but I can do B dot C cross A. I can even do C dot A cross B. Okay. And that's what I'll do. And then I'm going to get a convenient form and then flip the sign so that I get a negative. It's always helpful when you know the answer. That's not true. People struggle without knowing the answer. And what we're doing is a cleaned up version of presentation, right? So then, d phi dt equals, again, you're integrating over the ribbon. I'm going to do dl dot b cross yeah? Okay, and of course, I'm going to change the order of the dot product. Well, that doesn't do anything. But I'm going to write this as V cross B. because after all, magnetic force is QV cross B. Now, mind you, charges here, there could be a current in the loop, so charges could move in this direction. So it could have, so if you look at the charge, a typical charge here, it could have this velocity V and this velocity U. I should have done it sooner. My apologies. So the net velocity is what? But no harm done. Net velocity, I'll call it U. That is V plus, no, I'll call it W. Yeah? I want this, and in fact, I'm glad it came out this way, so you can see why the thought process evolving in this, right? So, if I want magnetic force, I want net velocity cross B. We don't have net velocity cross B, but that's okay. It's easy for me to fix because I can erase on the chalkboard. Look at what I'm going to do, and you have to tell me why I can do this. Obviously, the addition gives a zero contribution. That's why I can do it. Look at this. dl over here is that. And if you have a velocity along the current, u is also along dl. So if you take two parallel vectors or anti-parallel vectors and take the cross product, what do you get? 0. So I replaced this with W. With apologies, I'll continue to do so here. And I apology only because of your note-taking. But this is precisely force per unit charge, the magnetic force per unit charge. Right? There's no other electric field here. So isn't this exactly the expression for the EMF? And so this is always true. Whenever a loop goes through a magnetic field or a magnetic field changes along. So if a loop goes through a magnetic field, there's a change in the amount of magnetic flux. Yeah? Whenever that happens, and there's a time rate of change, then it induces an EMF. Now, in some sense, you can forget all the details here, and let me tell you story. It doesn't matter how you create an EMF. Again, I didn't show this, and if you want after today's lecture, I could show this. It's only a minor modification of this proof. But it's true if the circuit is not moving, but the magnetic field is changing. So suppose I do this. And there's a very important lesson to be learned here. So this is my region of magnetic field. Let's say it doesn't matter, but let's say it is this. And I have my loop here. Maybe connect it to. Okay? Of course, if you pull on the loop, you know there's a motional EMF. But now, since we have stated that the theorem is true in general, what I'm trying to say is, suppose this B is a function of t. The mere fact that it's a function of t, it creates a change in flux. And that creates an EMF. The most important thing to remember is this little confusion. And this is the only difficult aspect of these problems. What does that minus mean? Which way is the EMF? So EMF is like a battery, right? So that means the induced, so this is an induced EMF. Okay, so pay attention, this is really the only point of confusion for students. The question is the EMF, is it like the battery is this way or the battery is that way? And Griffiths has a nice way of putting it to explain this negative sign. He says, nature abhors change. It doesn't like change. So if you have a magnetic field increasing in this direction, okay? So let's do this, and I'll draw the diagram accordingly. Suppose B of T increases into the board. I have two ways of inducing an EMF. The battery could be like this. That means the current flowing like this. You know, if you induce an EMF in a current carrying wire, you're going to get a current. Or it could be like this. Well, which one is it? Well, so this will induce a current. And if the magnetic field is in this direction, the induced current is, not the magnetic field is in this direction, because the flux is increasing in that direction, the induced current should be such that the magnetic field induced by that current opposes that. So if I pick the battery this way, and this is wrong, don't pick it this way. If I pick the battery this way, the current is flowing this way. Which way is the magnetic field induced here? Into the board. But that is precisely the direction in which the magnetic field is increasing. So the correct answer must be this is the direction of the induced EMF. But it's rather fantastic that you have a change in magnetic field, somehow you can create voltage. And voltage is electricity. So if you have a time-dependent magnetic field, you may have just created an electric field. So remember, this is finally electrodynamics. So electric field and magnetic fields are not two different things. Yeah? And who says what is time dependent? According to relativity, if you are measuring a magnetic field, and if I'm moving around, the magnetic field or the magnetic flux I measure may be time dependent. Although if you hold a ring, it's not time dependent, but if I hold it and I'm moving, it could be time dependent. So there's a greater story here that one cannot say, well, this is magnetic field, I'm going to put it in my left pocket. This part of it is electric field. No. One can bleed into the other. Okay? And there's an analogy of this in between space and time as well. One man's space is another man's time. Not metaphysically, but physically. Well, all that talk, we need a little demonstration. So, a theorist doing demonstration is never... Yeah, exactly. So I have a solenoid because and a magnet. Yeah? And I can, I'm going to do this first. Nothing's going to happen. Nothing should. Yeah, good. Why is nothing happening? First of all, it's 0.001. Yeah, that's instrumental problem. Nothing's happening because there's no rate of change of anything. But if I pull this magnet out, the magnetic intensity goes to 0. So there's a change in flux, surely. It's going from something to 0. So that better induce a voltage. Yeah? I told you. Maybe this is not sensitive enough. That's good. Am I on voltmeter? Lower sensitivity. No, you saw it already. But so moving magnetic field creates an EMF. If you run on a pedal, you can generate electricity. That's the principle. That's how motors and generators work. And I mean, this also should move it fast enough. Now, see, if I do this, it may not catch it because the time rate of change. So magnetic field is increasing, but the rate of change, well, still within sensitivity. It's not that, but if I do this, there it is, it spikes. Always happy when physics is not just theoretical. Yeah. So let me do one. It has drastic effects as well. And so if you have a magnetic field, it can, moving magnetic field, it can generate an EMF. And if you have an EMF, you can, there's an electric force on it. So there could be a force acting on this. So there's there's an effect called eddy currents. We won't spend too much time on it. Perhaps I'll even bring a later demonstration. So you can see a copper wire with, you can see there's a piece of metal in here. Well, come on. Yeah, it just falls, like it should. The other force, gravity, right? But now, you can see it falls like, there it is. But now I'm going to take a magnet. And you can see, because the current's created in the metal, and there'll be forces acting on it, the fall is going to be slowed down. Very slow. Can you see it? Just slowly going through. So you can yeah, it's not 9.8. You can actually measure it very easily. So there are incredible effects, and all of these things, every one of these effects have huge amount of practical uses. Yeah, this could even be magnetic braking. Yeah. So, and that's a good thing about the electromagnetic field. Let me make sure it is somewhat straight. Well, that requires glasses. Remember. Delete this part. Okay. As long as I'm deleting, let's figure out the problem that I'm about to do. Problem 713. So this is problem 713 from the textbook. So here you have a loop. I should have drawn a resistor. All loops have resistors. And it's a square loop. A, and some sort of a resistance. And there's a magnetic field acting on it. B, Y, T. It depends only on the y-axis. And this is the origin. And it's given by K y cubed T squared Z hat. And it says find the induced EMF. Okay? Again, induced EMF is not that difficult to find. The difficulty is saying which way is the EMF. So first of all, which way is the flux increasing? In the positive Z axis. So which way do you think the induced EMF will be? Will it go clockwise or counterclockwise?
Such that it goes into the board, so clockwise.
Clockwise. So this is a good way to indicate that it's an induced EMF. That's the direction. So if I give you a problem like this, if you have the direction shown, there'll be partial credit for that, because that's the most important part. The rest is just calculus. Oops. Minus d dt of b k y cubed t squared dx dy. Correct? And they both go from 0 to A, 0 to A. Please make sure that I'm not making a mistake. I can bring my k outside. The derivative of t squared is 2t. The dx integral I can do, that is just A. And then, well, we're getting very cocky here, so 0 to A. Correct? So minus kt over 2, because 2 and 4 becomes 2. I would have, what, a to the 5th? That's the, and it depends. The EMF keeps increasing with time. Of course, the intensity in any real circumstance is not going to increase as t squared forever. Otherwise, you'll get infinite voltage. Okay, so now we can modify the set of equations for E. So unless you have a battery or something else in the system that is creating an EMF, in general, EMF, if there's nothing else, this is really an E. It has evolved into some sort of a psi or sigma, or not sigma. It's just a script E. This is, what is that? E dot dl. Yeah? So, a closed loop. So what we have is E dot dl is equal to minus d dt of B dot dA So I can do two things. I can use Stokes' theorem and do this as del cross E dot dA. So that means both integrals are del cross E. And now for a fixed loop, right? It doesn't even have to be a loop. It could be just a closed loop in space. Yeah, at a given time. this is minus okay? So let me explain this diagram, this set of equation. So suppose you have a region of B. I'm taking a closed path. This one is, so let me put this here, this is so asterisk, and any closed path at a fixed time. That's what I'm doing. So look at that. The dA does not suffer a derivative. That this is true. So it's almost like your Gaussian pillbox. You can pick any pillbox you want. You can pick any Amperian loop you want. In a similar way, this is not necessarily an Amperian loop. I'm just going to pick a closed region in space.
So when you said it doesn't suffer a derivative, what is that?
Oh, meaning, see, if
DT doesn't see,
yeah, if area is changing in time, you have to take the derivative. You have to use product formula. No. This is at a fixed time.
Yeah.
This is true. And this is true for any loop. So this any is very important here. It is true for any area. It doesn't have to have a circuit. Yeah? This is true for any area, and so the integrands must be equal. Therefore, del cross E is equal to what? Minus dB dt. This is the integral version of that. This is also referred to as Faraday's law of induction. You can induce an electric field. Up until today, starting last August, del cross E was 0. Yeah? This is a definite shift. It also tells us that they affect each other. So now our laws of electrodynamics look like this. Divergence of B is 0. Del cross B is mu 0 J. Divergence of E equals rho over epsilon naught. Del cross E equals minus dB dt. A time derivative in B creates an electric field. This is almost Maxwell's equations. Maxwell's equations are the equations that govern electromagnetic phenomena. Almost. What could be the only modification?
Wasn't there like the space kind of?
That is remembering. Don't remember. What's good for the goose is what's good for the gander. So if a time derivative of B can create E, yeah, and that's exactly what it is. I forget the constant, but I know. And that'll complete the story. This will be electrodynamics.
And then the magnetic monopole.
No monopole.
When we find it.
Can't find
We're
it.
gonna
Yeah.
find it.
Yeah.
Spend my life on it.
But don't write this. We haven't entered into conversation. Yeah. There are easy way to find E under certain condition. So over here, we know that Biot-Savart's law, B equals mu0 over 4 pi integral of what? J cross r hat over r squared d tau. So, if you look at this, when rho is 0, only if there are no net charges, you can say that E equals negative 1 over 4 pi dB dt and I should have put prime because you're integrating over sources. Here there are no sources but the magnetic field, so yes, still you're integrating over all the magnetic field. The time derivative, the rate of change of magnetic field everywhere. But this is only true when rho equals 0.